Hi, everyone. How are you all doing? I hope, we hope your reInvent is going amazing. Good afternoon, and we welcome you to today's session to learn about Windows containers on AWS, and more specifically, to learn about how our customer Carrier Global improved their cost by 40% while using Windows containers and specifically using Amazon ECS to run their Windows containers. My name is Purvi Goyal, and I'm a principal product manager at AWS, focusing on customer experiences for Windows customers for the last 6.5 years. With me is Glenn Buchholz, who's a very talented colleague of mine from AWS, and a very special guest, Matthew Burt, all the way from Carrier Global.
My name is Glenn Buchholz. I'm a principal solutions architect with AWS, and I specifically help customers modernize efficiently. So with that.
Hello, everyone. My name is Matthew Burt. I'm a senior manager of cloud engineering at Carrier. I had the privilege of being part of this company for the past 7 years to drive part of our digital innovation and software portfolio migration to the cloud.
Thank you, Glenn, and thank you, Matthew. Let's get started with today's session. We hope you're just as excited to learn about it as we are to share. Let's start with a quick poll. By a show of hands, how many folks in the audience would consider themselves power users of Windows containers? Just as well, okay. And how many of you are somewhat familiar with Windows containers or are using them in a limited capacity? Okay, some of you. Great, well, we hope there's something for each of you to learn and take back from today's session. Here's a quick agenda for what we're going to be talking to you about. We'll start with a quick background on what containers are. Of course, we have folks in the audience who are not familiar with the technology, so I'll give a quick overview of how we've seen compute evolve. We'll also talk about why Windows containers specifically. What are the top use cases we see customers use Windows containers for? And of course, we'll get to the core of today's topic, where we learn about how Carrier Global evaluated their workload, moved over to Windows containers, what were their business objectives of doing that, and what were the multiple iterative solutions that were implemented at Carrier to achieve the results that they did. At the end, we'll also have Matthew talk a little bit about where Carrier is headed with Windows containers, how they're planning to further improve their application and its efficiency in the future. Then we'll share a quick list of resources for you all to get started with Windows containers on AWS. And of course, we'll have a live Q&A at the end for you to ask any questions you may have about the topic. Sounds good? Let's start. So here's a quick evolution of how we've seen compute platforms transform over time. Of course, this traditional data center where you ran applications directly on physical servers, the operating system, libraries were all allocated to these physical servers. You had complete ownership and management responsibilities of the underlying hardware, and there was no way to define resource constraints for your application, which of course led to resource allocation issues. Naturally, as a solution to these issues, virtualization was introduced. Virtualization allowed you to run multiple virtual machines, or VMs, on a single physical server. And each VM is a full machine which consists of various components, including operating system, file system, libraries, etc., and on top of the virtualized hardware. Virtualization also allowed for applications that are running within these VMs to be isolated from one another. And now, of course, we see a shift towards containers to package and run your applications across a diverse set of environment, both on-premises and on cloud. So containers are similar to VMs in that they have their own file system, they have their own shares of CPU, memory, and other resources, but have a little more relaxed isolation properties to share the operating system across applications. Containers are also decoupled from the infrastructure and are considered lightweight, which makes them portable across cloud and OS distributions. Let's see a few benefits of running on containers. As I mentioned, containers offer an isolated environment that makes it easy to develop, deploy, and manage applications. It also makes it easy to automate dev lifecycle stages be it dev, test, or deploy, and leave DevOps team more time for innovation. Containers are also a useful tool to improve application density and overall resource utilization. They're also more efficient than VMs, which offer better isolation and reduce the overall deployment time and management costs. Naturally, containers are also very easy to start, and they also start and stop quickly, which makes them useful for applications that require fast scaling, cloud bursting, and fast expansion. All right, well, that's great. Now you must be wondering, containers are great, they have a ton of benefits, but how and why do they make sense for your Windows workloads? We often see customers try to use Windows containers to modernize their old legacy applications to improve their portability and longevity. Now, be it your .NET Framework applications running on older versions of Windows OS, or be it Windows services such as WCF, MSNQ, or IIS and ASP.NET web applications. Containerization offers a low effort to modernize these applications and improve scale and efficiency of your workloads. When running and operating your Windows Server VMs, you often needed to worry about endpoint protection, backup solutions, and worst of them all, the blue screen of death. With containers, all of this goes away. A lot of you also must be using or running commercial off-the-shelf or third-party vendor applications, which you have limited expertise on. Running these applications on containers offers an ease of maintenance for these applications. We've also oftentimes seen customers use Windows containers in the online gaming industry, in which case they want their applications to scale up and scale down quickly and are trying to get away from managing infrastructure. All right, well, now that we've talked about what containers are and why Windows containers, I would like to welcome back Matthew and Glenn to talk about Carrier Global, talk about their use cases, what their problems were, what their challenges were, and how they came about using Windows containers. Matthew, over to you.
Thank you, Prithvi. So a few words about Carrier Global Corporation. Founded in 1915 by the inventor of air conditioning, Willis Carrier, we proudly stand as a prominent leader in both the HVAC and transport refrigeration industries. On top of delivering amazing equipment, the company's mission is to provide digitally enabled lifecycle solutions for the benefits of our customers and the planet to become the global leaders in intelligent climate and energy solutions. So to promote our highly configurable product, so a few words about AWS and our partnerships. AWS serves as our preferred cloud provider, collaborating with us to deliver exceptional cloud-native solutions, such as Abound for healthy building and Links for the connected cold chain. We built a great partnership with AWS since 2020 and leverage many of their services to promote these solutions and also migrate our current software portfolio to the cloud. So in our century-long journey of product innovation, we cultivated a rich legacy of product innovation. And with this legacy comes the responsibility of nurturing and upkeeping our existing solutions. Our story today is about our commercial HVAC sales tools, ECAT, used by all our salespersons across the globe. To promote our highly configurable thermodynamic product, we built a tool in-house in 2002, harnessing a model-based design calculation engine. This engine forecasts unit selection performance according to customer requirements. At the time, our team constructed a monolithic desktop software using Fortran and VB6. So the software was working great on salesperson laptop, but wasn't inherently designed for the cloud era to work on any device from anywhere. So in 2016, we embarked on the journey of modernizing our sales tools with the vision of transitioning it to the cloud. Recognizing that a complete overhaul of the solution was not going to be quickly feasible, we opted by decoupling the architecture into different services and build a modern web user interface using React on top of it. Presently, we are diligently advancing the modernization of each of these components one by one using containers in our pursuit of achieving a fully cloud-native solution. So one of our major challenges is the calculation engine, written mostly in Fortran with deep dependencies with COM components and the Windows operating system. In our modernization journey, we started by implementing a custom load balancers, talking to different IaaS servers, each of them hosting a dedicated product calc engine. Calculation requests could take up to a couple of minutes, and we knew that it was not going to scale as we needed. So most of the time, also, the server were not used, and we know that during peak time, some of them were overloaded, slowing down our users while increasing cloud cost. And to address this, we knew that containers and containers orchestration was a good solution. And in the context of our partnership with AWS, we reached out to them to see how we could leverage these services to improve the architecture without changing the code base for now, and which was quite important for us. So let me pass the torch to Glenn, who led this initiative named EBA, to give you some insight on it.
So a quick show of hands. For people who have worked with AWS before, how many people are familiar with the term EBA, or Experience-Based Accelerator? Okay, some people. So let me explain what that is before we delve into our solution. The reason being, technology alone is not what solves problems, people do. And in experience-based acceleration, so you may know that our CEO is fond of saying there is no compression algorithm for experience. That may be true, but through the experience-based accelerator, we can line you up with the right experiences to make sure that you get to your business objectives faster. So what is an experience-based accelerator? The way that I mostly articulate this to our customers is that you think about something that you need to get accomplished, and then imagine your engineers surrounded by AWS experts to help you get there. Now that's a little bit simplistic, but to dive deeper, the first thing we do with an experience-based accelerator is we set concrete success criteria that can be measured by quantitative goals. We then work backwards from those goals that are set through collaboration with AWS and you, the customer, and we use an agile planning methodology to come up with stories and milestones to get us there. This whole process takes about 3 to 6 weeks just for the planning. Now, the reason why this can take some time is that those experts that we're going to have working hand in hand with your engineers, it takes time to acquire resources from both our side and for yours. We also want to make sure environments are prepared and roadblocks are removed. Because at the end of the planning cycle, we have a 3-day period of what I call furious implementation. And we do like to make this fun. We call it a party. And we all get together with all of the resources ready. And then we work towards those clearly defined objectives we set in the beginning. And at the end of the 3rd day, we use those quantitative metrics to grade ourselves. Did we do well? Did we not do well? And so that's the underlying way that an EBA works. It allows us to bring expertise to you. In most cases, we're working in advisory capacity. So solution architects like myself are advising your engineers. And this is the point, because we want you to learn from the experience, not have us do it for you. So we're there to provide guardrails and advice, but still, it's an experience-based accelerator. To get the experience, you're doing the work yourselves. So let's talk about the first EBA with Carrier. What were those clearly defined success criteria? The first was we needed to containerize the application. The engineering group we were working with at Carrier had some experience, but not experience necessarily with Windows containers on AWS. And goal one was simple: containerize the application. Also, really easy to measure, right? Two, it's not enough to just containerize the application. If I do it by hand on my laptop, that's not very reproducible. That's not very scalable. So the second objective was to introduce this containerization packaging and process into their continuous integration and continuous delivery pipeline, their CI/CD pipeline. This would ensure that moving forward, the learnings were enshrined in code and repeatable, and they could scale it out to other projects and templatize it if they needed to. Lastly, was scaling. Now that we have everything inside a container, we want to be able to scale to meet the needs of the people in the field that are using the service. And so we wanted to make sure that we had an orchestration framework, in this case, Elastic Container Service, ECS, configured in a way that would appropriately expand and contract resources as necessary, so we weren't just provisioned for peak. So what you see here is the end state architecture. So I'm going to quickly explain what each service does, but I'm also going to tell you this was not the architecture that we started with at the end of our planning phase for the EBA. So one of the things that I want you to realize is that when you're working with the experts or people that have experience, when something doesn't go as planned, we can quickly pivot and still reach success. And that's what this diagram represents. So let's unpack what's here. First, we have the containers, of course. They are packaged in ECS tasks. The ECS tasks are running on EC2 instances. Now, one of the reasons this is important, and this is where the power of Windows containers on AWS comes into play, is that we wanted to be able to implement this more cloud-native architecture without refactoring the application. So if you remember from Matthew's description, the application was VB6, and that limited us to a particular Windows core container with dependencies. And through using Windows containers, we're now able to use ECS, which gives us our scalability. So that was Windows containers. Those are tasks. The scaling we were envisioning would be accomplished by auto-scaling groups in EC2. The database that would store the results of these calculations, we were connected to through Direct Connect. And then you'll see out in front, and Direct Connect is a physical connection between the AWS service and the resources, so it's physical fiber. And then you have SQS and Amazon API Gateway. Amazon API Gateway is a place for you to connect to using HTTP to deliver the payloads and manage that API interface. And SQS, the simple queuing service, is a place for those payloads to exist persistently until the calculation engines can process them. So the way that this would work is that somebody in the field would have a request for one of these calculations. They would use their client, which would then send an HTTP request to API Gateway. API Gateway has an integration with SQS. It would create a message and automatically put it on the right queue. And then the tasks would sit in the background, process the information, and write the results to the database. Now, as I said, this was not the final result. Originally, we had something more similar to what you saw in the first slide with the layer 7 load balancer. But we noticed a problem. Each one of these tasks would have their own queue. And each one of these tasks have a different processing time. Some would process really quickly, and others would take a minute or two to process. But when you're dealing with the layer 7 load balancer, you're doing round robin, and you're putting these calculations of indeterminate length just, putting them across all of the different tasks with no rhyme or reason. What was happening is that tasks were being processed that would take minutes, and they were still receiving traffic. And those other tasks may only take 20 or 30 seconds or 5 seconds, but they had to wait. Because when the layer 7 load balancer received the message, it had to immediately get rid of it and give it to somebody. But with round-robin load balancing, it doesn't know who is or isn't free. So it was just going to the next task over and over again. And this was resulting in poor user experience. So what we did was we removed the layer 7 load balancer and used the API, gateway, and SQS integration instead. Now, we had to make a small change to the code surrounding the VB6. So instead of listening on port 80 or 443 for an HTTP request, now it was polling SQS instead. And the advantage here is that it would only poll and pull work from the queue when it was free. So work would go to the queue, and it would be processed as soon as possible by the next available task, resulting in an overall better user experience. And we were able to make that leap because we worked collaboratively, AWS and Carrier, to get to that end result. So Matthew, we're able to containerize the application, provide an overall better user experience, and scale according to queue size. So was this good enough?
Well, before I talk about the result itself, let me share our experience with this EBA, right? Using Windows containers was really exciting for us. And our team really appreciated the opportunity to use this technology to improve our architecture as part of our cloud migration journey. You and AWS helped us tremendously to navigate through the different implementation choices we had. And we managed to implement the solution without much difficulties. And at the end of the EBA, we already got some pretty good results, right? So the first one was the fact that the deployment was more than 16 times faster. That was like mind-blowing for us. 3 days, 16 times faster. The second was that the solution saved us 1/7 of the original infrastructure cost. And the last one was the solution was sending way less error message to our users, improving drastically salesperson productivity, and give them more time to focus on our customers. So to answer to your question, we were really happy with the results, but come on, we knew that now we could do more, and we could push the boundary further. So we wanted to focus on 3 main topics. The first one was, how can we scale even faster? And scalability is important for us because we don't want our users to wait for the calculation response. And we want them to have the answer as fast as possible. And we don't want the scaling process in the middle. The second was, how can we improve our time to value with the faster deployment that we have now and improve that even better? And the third one was, how can we generate an even better cost efficiency? So this is why we started a second EBA to push on this.
So let me see if I remember correctly. We want to have even more cost efficiency. We want to scale faster. And we want a faster time to value, which means we want to be able to deploy faster and want to be able to see our development code changes faster. And this all came out of the first EBA. Now, EBAs, I like to say that they're not the end when they're done. They're the beginning of something else. And whether you choose to adopt this process internally or work with us again on a second EBA, I want to keep in mind that this process is iterative, and we're forever iterating toward a better experience for your customers. So now that we have our 3 success criteria for the second EBA, what did we need to do? We needed to first address cost optimization. We had to take a look at the operational data and figure out how could we do more with less. So one of the things that I'm going to tell you now that I left out in the description of the first EBA is that the calculation engines were stovepiped. Each EC2 instance that we created for the ECS cluster could only process one type of calculation. So we had to have different AMIs for each different type of calculation that we had to do. And this was resulting in the scenario that you see up on the board here. If at a non-peak time, you have two EC2 instances that have to be allocated for each calculation engine, but only 4 calculations coming through, even though you have a total capacity of 12 calculations, that's what you're stuck with. You have to over-allocate on EC2. Now, what could we do about this? Well, that one VM of wasted capacity seemed to be the prime target, and we focused our efforts on figuring out how to eliminate it. Because we had invested in Windows containers on ECS, we had already started adopting more cloud-native services to help with making ECAP more efficient. So why not add another one? So the process of containerization gave us access to technology and tools, specifically Windows containers on ECS, gave us access to technology and tools that we wouldn't have had in our tool belt earlier. And in this case, we added one more service, Amazon Event Bridge. So the key thing here is that Amazon Event Bridge has integrations with both API Gateway and ECS. And what Amazon Event Bridge does is it allows people to subscribe, and I'm going to oversimplify this a little bit, but it allows people to subscribe to see what's going on with other services in AWS. And in particular, we wanted ECS to know what was going on with API Gateway. And EventBridge would pass the messages, and we would be able to do things with those messages. Now, each one of the different calculation types was coming in on a different URL for API Gateway, and that was information that could be conferred through EventBridge. What we could then do is use the native integration between EventBridge and Amazon ECS to spawn only the type of calculation task that we wanted to do as it came in, and then that calculation task could go away when it was done. So in the earlier diagram, when those tasks were spun up on an EC2 instance, they would stay running because why not? The EC2 instance is already running. But now we could start to figure out what tasks could run as needed as the payloads were coming in. And then we had another idea. Why didn't we make it so that a single EC2 instance could run any type of task? And I'll go into some of the changes about that later, but we used Amazon EC2 Image Builder to put the appropriate containers on the AMI preemptively so that that could happen. And so now we took a 20-year-old application, and we were able to use Windows containers to elevate it to being an event-driven, almost cloud-native application. So what was the result of turning this into an event-driven cloud-native application? We were able to eliminate that VM of wasted capacity. Now, in the same scenario, we're able to run any task on the EC2 instance. We knew which tasks we had to run due to EventBridge. And we reduced the amount of over-provisioning from one entire VM to one single task. And that's what gave us our cost optimization savings. We were doing more with less. We noticed something else. So originally, when I showed you the event-driven architecture, I said the task would spin up and then go away. Now, if you know something about containers, maybe you do, maybe you don't, but the containers have to start, right? And when applications and containers start, there's a small penalty that's paid. Now, if everything is up and running with containers, the penalty is small, but it's still there. but then the application has to start it as well, and that varies. Now, the engineering team at Carrier had done a good job, but the penalty was still there. So we asked ourselves a question. How likely is it if that we have a task of one type coming in, or a calculation of one type coming in, that there's another one shortly behind it? What if we could get rid of that startup penalty? So what we did was, before the task terminated, we said, before you go, check to see if there's something else on the queue and process that as well. Now you may ask yourself, but you've just spun up 2 tasks, and that's okay, because the total time that the second task, which is going to be discarded when it realizes there's nothing on the queue, you pay in terms of resource utilization is very small. But the benefit to the end user of having their task or calculation being processed almost immediately gives a better service to the people using the application. So you spend a little bit of money by running that task for maybe a second, but that's really not a lot compared to the benefit that you're giving the end user with faster response time. So by having the expertise of both Carrier and AWS in the room, we're able to find that optimization and go there as well. So the next thing we needed to do was faster time to value. So faster time to value means when I make a change, how quickly can it be utilized? And in particular, we were focusing on both developers seeing changes to their code faster and developers being able to deliver functionality to end users faster. And this is what we took a look at. We were initially using Amazon EC2 Builder as a way to package and deliver the code to the ECS cluster. But Amazon EC2 Image Builder is concerned with the processing and creation of an entire Amazon Machine Image, or AMI. But the changes that we were making on a daily basis to the code were just in one single container. So the Amazon EC2 Image Builder process, because it has to do more, because it's concerned with more, wasn't the most efficient fit for this model. The first thing that we tried to do is we tried to follow the best practice given by most container guides, and that is start with an empty AMI or an empty EC2 image, and then pull all the containers you need and run your application. The problem that we were running into here, so for reference, the Amazon EC2 Image Builder was taking 45 minutes to deliver the code to the development environment. When we did that, it took 11 minutes, which was better, but we had a problem. This would also mean that it would take 11 minutes to scale up every time we put a new EC2 instance into the ECS pool. Currently, we were at between 4 and 5 minutes to scale up. So while we had achieved our goal of delivering faster time to value by 4x, our other measurable goal of scaling up quickly, we didn't succeed. So let's take a look at the other side of the diagram. We use the Amazon EC2 Image Builder to once a month, when Microsoft patches come out, rebuild just the server core image and the software dependencies containers all into the AMI, leaving out the last bit of code, which is only about 0.5 gigabyte. And this is just for the development environment. Then these images would go out into the ECS cluster, and then through naming convention, the right image would be pulled down, and it would take less than a minute, 2 minutes. And now we could see the results in under a minute when going through the CI/CD pipeline. And this would allow the developers to see their changes 40 times faster than when we originally started. Lastly, when we go to QA and production, we do put all the containers in the AMI, so we don't have to pay that extra minute for scaling, because remember, we're also trying to optimize our scaling as well. And that's how we were able to achieve faster deployments and faster time to value. Now we wanted to talk about faster scaling. So we talked about the customized AMI already. We achieved that by putting everything into the QA and production images, so we no longer have to do a Docker pull when the application starts up. But I want to talk about something else. In the Microsoft Windows operating system, Is anybody aware of what happens when you boot the first time ever as opposed to all the other times you boot? Has anybody ever heard of sysprep and update? Okay. When we were profiling what was taking a long time for us to scale up, we had noticed that the first time an instance would boot, it would take 8 to 10 minutes. But if we just turned off that image and turned it on again, it would take 2 minutes. And I started to dig deeper, and I found out about sysprep, when you prepare the operating system for the first time. And I said, man, I wish there was some sort of feature that could do that for you automatically. So it turns out that my colleague over here had something for me. This is called Amazon EC2 Fast Launch. And this is a feature where you're building the AMI or you're specifying the AMI. If it's a Windows image, it will go through that process first. It will boot the image. It will take a snapshot of that image. And it will hold it at the ready for when an EC2 instance is created for real. So this way you don't have to pay the sysprep and update penalty. So we save time there. And lastly, Amazon autoscaling, EC2 autoscaling groups have a feature called warm pools. And these allow you to boot an EC2 image up preemptively and then hold it in the stopped state so that it's ready to go, or you can even hold it in the hibernate state, but for our application, we held it in the stop state. So it's up and ready to go quickly when one of your CloudWatch scaling watermarks is violated, and it will go up. So with all of this, we were able to reduce the scaling time from 4 to 5 minutes, which was where we were at after the first EBA, to 2.5 minutes, which was more acceptable for the end user experience. So I want you to know that these results are cumulative with the first EBA. These aren't the totals. So this is an improvement on top of the first EBA. We were able to service the same workload with 25 less VMs. Because of the VM type and mix that we were using, we're able to save an additional 40% on cost. And we had faster, more efficient scaling when we were looking at peak times and peak loads. So now, we'll talk about what the future holds.
Thank you, Glenn. So we achieved a lot with these 2 EBAs, this event-driven architecture, and Windows containers. It is good enough for now to scale our application for future needs and future product while maintaining acceptable cost and even flat cost. We're super proud of this, and we think that Amazon AWS and Windows containers help us to get where we needed to be for now. So now we had the headroom to focus on the solution we want for our near future. At the end, we think that 3 main opportunity remains. The first one is about the service running on the calculation engine container. EC2 works great, but we need to optimize more the size of the instance used. Our goal is to waste less resources by fine-tuning the level of computation and memory required for our workloads. The second is about provisioning. Today, we need to keep some VM alive, even if the event bridge doesn't trigger any task, which still drive the cost up. And the third one is about the boot time. Even if it happens a couple of times per day, and we went from 45 minutes to 2.5 minutes, we still need to improve that a bit to make sure that nobody is waiting for an instance to scale. And all of these opportunities are part of our future plan to push the boundary and empower our business even further. By breaking down our application into micro front-end and microservices, we'll be able to maintain these services independently regardless of the new language, modern language we're going to use. Having smaller services will empower us to now use serverless technologies like Lambda to scale infinitely and only pay for the millisecond of use. So when I look at the journey we went through, moving from a desktop VB6 and Fortran app to a cloud-native solution and look at the future. I'm really proud of what the team has done and the result of this EBA and architecture. They solve a major challenge and a major roadblock in our migration journey. And I think that you should definitely look at this process and this technology if you have similar use cases. Back to you, Prithvi.
Thank you, Matthew, and thank you, Glenn. Well, we all saw how Carrier Global achieved significant improvements in costs, speed, and resilience, not just by moving to Windows containers, but by offering iterative improvements and using number of different capabilities, using Event Bridge, API Gateway, Image Builder, and EC2 Fast Launch. If you all want to read more details about what were the details of moving to Windows containers for Carrier Global's workload, here's a case study that you can save the link for and review it later for more details. But for now, let's close on today's session by talking a little bit about how AWS offers one of the best places for you to run your Windows containers and how you can get started. As you see here, AWS currently offers one of the broadest set of compute options to run your Windows containers, ranging from all the way between AWS managed and self-managed orchestrators. If you are somebody like Carrier Global who has limited expertise on containers, you can easily get started on something like Amazon ECS or Elastic Container Services to run your workloads, to run your Windows containers. You can also run your workloads on ECS anywhere for those workloads that require low latency, and you can run these workloads on premises using ECS orchestration. Now, for those who are familiar with Kubernetes and who would like to use that platform to run their Windows containers, we also offer Amazon EKS or Elastic Kubernetes Service to run your Windows workloads. If you want to have full control, you can go all the way from from self-managed Windows containers on EC2, VMware, and Outposts, to all the way to completely AWS managed container services like AWS Fargate that we'll talk about a little bit later. Our goal at AWS is to offer you maximum flexibility so that you can pick the best option that meets your needs and the workload's needs. Now, we have supported Windows containers on AWS over the last few years now. And over these years, these platforms have evolved to offer you the best performance and resilience. And we also have offered a number of different capabilities to improve your customer experience, such as GMSA for authentication, both domain join and domainless, Windows FSX support, various logging and monitoring capabilities, and more recently, auto-scaling improvements, and the list, of course, goes on. We at AWS, of course, strive to make AWS the best place and most easiest place for you to run your Windows containers. And in the light of this, in 2019, we launched a tool called AWS App to Container, or A2C, that enables customers to re-platform their Java and .NET web applications into containers. A2C analyzes supported applications, containerizes them, and creates container images so that these can be automatically deployed to Amazon ECS or Amazon EKS. We also offer fully managed container platform, which is AWS Fargate. So in case you have workloads where you don't want to manage your infrastructure at all, or don't need to worry about scaling up, scaling down, or patching even, Fargate is the way to go. And you focus on your application, and AWS essentially takes care of the rest. Additionally, we also offer a ton of hands-on workshop and training content, which we'll share the link to in just a bit, that can help you get started. We'd like you to save these links for future. The first one contains the links to the hands-on workshop, as I was talking about, which has a number of labs that you can follow through and really learn how to get started and how to use Windows containers in the most optimum manner. The second link there that you see is a repository of all the helpful blogs that we have created over the years, which talks about detailed steps on how you can use various capabilities and also keep up to date on the various improvements that we continue to make in these platforms. Last but not the least, you also see the third link, which contains a self-service repository of guidance that details cost optimization strategies for running Microsoft workloads on AWS. And of course, it includes Windows containers as well, and it's called MACO, or Microsoft on AWS Cost Optimization. Thank you, and hope you have a great rest of the evening.